Okay, so yes, welcome to my talk about a new feature of the standard library, our Autodiff macro. So I generally care a lot about doing all types of compute stuff in Rust, so like high performance computing, machine learning, scientific computing. And one of the things which I was really desiring for some of those projects was automatic differentiation, and we now have it fully upstream, and I'm working on enabling it for nightly builds. So here's a small introduction on how that's going to look like. So first, for those of you who haven't heard before about AD, it's a feature which is mostly used for, like, for example, training neural networks, but also in a lot of other scientific applications like climate simulations. We had to do a couple of compiler changes for that, which I briefly demonstrate, and where we already talked about benchmarking before. So I'll show some of the performance features, which are quite interesting. So first, what is Autodiff? It's a new macro which is really experimental. So even after building the nightly compiler yourself from source, you still have to add this Autodiff feature. And then if you have a nightly build, can use the standard Autodiff macro, which is something which you can just apply to almost any function out there. Whatever you've been written in the past, it doesn't matter if you use any dependency or any crates, if you define your own types, we should be able to handle almost all of that. Except if you write inline assembly, but I'll get to that later. And yes, so for those of you, a small refresher of what derivatives are. So if you have a really simple function, x times x, the derivative of that is 2 times x. You might remember, like, if you take the derivative of sine, you get cosine and so on. So we don't really care, of course, for like these small toy functions in real world applications, but that's just a demonstration. We are working on a compiler level, so we are able to handle almost arbitrarily complex programs in reality. And now what you do is, if you apply such Autodiff macro to your function foo, then you first give it the name of a new function which we're going to generate for you. So it's just magically there. You don't have to worry about where it comes from. Then you are able to specify a couple of parameters. So for automatic differentiation, there are different types of AD. It's forward mode, reverse mode. The question is just like, how many input parameters do you have? How many output parameters do you have? For neural networks, for example, you usually use something called reverse mode, so that's what we have here. And then in the case that you have more than one input and one output argument, you're able to specify, like, hey, for like which input to which output you want the derivative. We do support things like MPI, GPU programming, batching, partial derivatives, custom derivatives. So if you've been using Autodiff in other languages, like for example JAX, you might recognize some of those terms. And yes, so once you've applied the macro on the compiler side, we're going to take care for you that this function bar suddenly shows up. You pass your input arguments to it, and now suddenly, out of thin air, we have some extra output. So instead of just returning one float, we now return 2 floats. The first one is just whatever output you've been originally computing. So in this case, x times x, but the new addition output is the derivative. So in our case, 2.0 times x. So you get 6 or 8 there. Now, how is it possible for us to have an Autodiff macro in the standard library, which is actually like state of the art? The shout out for that usually mostly goes to LLVM, which is the default compiler backend of our Rust compiler. So whatever Rust code you write, the Rust compiler itself doesn't do most of the optimizations. We do a lot of checks to make sure that your code is correct, but at the end of the day, we're going to lower it down through a couple of different stages to LLVM IR and let just the LLVM framework take care of that. So shout out to them for most of the things. Another thing which we have to consider is on why AD is fast is, well, first, automatic differentiation is kind of complex. We do heavily rewrite all your code. We like duplicate your code size in reverse mode. We had a lot of data dependencies here and there. And if you think about it, compilers at the end of the day just also like programs, they run out of energy. Like if you give an input to a compiler which is too complex, you've seen compile times of the Rust compiler itself. They're sometimes a bit slow. In our case, it's even worse. Like if you start duplicating the code and add all of these dependencies, LLVM will just run out of energy. So you don't want to wait forever. So that's something to also keep in mind. And with that being said, one of the pretty classic examples for AD is neural networks. So if we look at a neural network, like you have a couple of input layers, you have some hidden intermediate layers, and then you get an output, which in our case might be classification, like cat, dog, whatever. And I mean, if you just load a neural network, like initialize it from 0, that's not going to do much. So the interesting how do we train a neural network? And that's where automatic differentiation comes in. That's where you like just implement your whole neural network, your inference in Rust, put the Autodiff macro on top, and suddenly instead of just doing inference, you can also do backpropagation, which gives you all the gradient updates. So after running your neural network, you know how to update your weights for a little bit to get slightly better results. And under the hood, what automatic differentiation does, as I mentioned, it duplicates your code size. So now suddenly you run from the beginning to the end. And once you're at the end, well, you go back to the beginning. So you run it a second time in reverse mode. That's where the name comes from. And beyond that, we have something called the tape. So to compute derivatives, you sometimes need stuff from the input or like from the beginning of your neural network, which has already been overwritten. So we might either be able to cache it, we might be able to recompute it, but at the end of the day, there's extra work going on. So that's how AD is usually slow in languages, because you just have so much extra things going on. And the normal compilation pipeline for all other AD tools is, well, you have some C code, we write it to some different C code, and then let whatever compiler backend you have do the work. Now for us, it's a bit more interesting. We have the Rust compiler itself, which allows for LLVM, and since we are an LLVM plugin, we have full control. So what we do is we first optimize our LLVM, which we got from the Rust compiler, to make it as small as possible. Then we run AD on something really small and easy. So now we duplicate the code size, sure, but I mean, it's just some really tiny program which is well optimized. And then since we generate a new code where we do want to run another opt run, just like for good measurements, because the code which we as an Autodiff tool generate, that code might not be optimized yet. So that's a completely different pipeline, and you can get it already through the Rust flags environment variable by passing -z autodiff equals enable. We have a ton of other interesting flags which you can check out, but that's the most interesting one which you need to enable Autodiff. So you see we are still quite experimental. And yes, with that you get the new binary which can now run derivatives. Now, we've talked about benchmarks before, and I've obviously been running some against the classic comparators like C++. And one thing which is really interesting for us is, first I've been implementing it in pure Rust. So we have an LSTM, which is a machine learning benchmark. We have Gaussian mixture models, fast Fourier transformation, bundle adjustment, and an ODE solver. So quite a range. And we, in almost all cases, if you look at the dark red one, Rust is doing pretty well. Now I also have a light orange one, because once in a while when I talk to people in other languages, they come up with, well, Rust, why do we really want to use it for HPC, for scientific computing, for all of that? You have all these safety overheads. Like every time you want to write something fast in Rust, you have to write it in unsafe Rust, right? So just as an answer to those people, I've been writing it using raw pointers. So we have no bound checks, and we also don't have any interesting metadata, because the safety which you get from Rust is also interesting for our LLVM backend, because we get a lot of metadata out of it. And you can see if you use raw pointer, we're actually so much slower in a couple of these benchmarks, like 2.5x or 10x slower. So just writing safe idiomatic Rust is usually the much faster solution if you care about automatic differentiation. And then there are a couple of things like fast Fourier transformation, where we're not fully there yet. The reason is just it's like a highly recursive algorithm where you keep splitting slices in half and then like shuffle elements around. So LLVM at some point just loses track of where to do bounds checking. It's a really easy fix, just like instead of doing a swap, you do a swap unchecked, and suddenly you have peak performance again and you match C++. But I mean, that's just the one case where we are actually slower by having safe Rust. So that's something I cared about. And then we have some other AD tools. I mean, in C++ it's the same underlying AD tool. They have the same compilation pipeline. So if you add the right metadata by hand, which we on the Rust side we get for free from the compiler, then you can match our Rust performance. If you forget to add the metadata on the C++ side, then, well, you are out of luck. Then you also have as bad performance as the raw pointers in Rust. And yes, so the next steps, I was originally hoping to actually be able to give a live demo on Nightly Rust. CMake was in the way. Some of you have been probably fighting it before. So we are working on enabling in CI once we fix all the remaining CMake bugs. I hope that a couple of people are going to test it out. We already received the first bug reports, which I was really happy from people who really compiled the Rust compiler from source, which, by the way, is super simple. There are like 3-line instructions if you want to test it out yourself. Right now, as you've seen, we do modify the compilation pipeline quite heavily, so we have requirements like fat LTO, which are even worse for the compile time beyond what we already do, so we hope to get rid of that soon. And yes, there's another project which I'm currently working on in the summer, like starting in 10 days. And And yes, that's for GPU support. We have 2 GSoC projects. So yes, thank you.